Okay, ladies and gentlemen, the second part of topic 12 is going to be plate tectonics. And whenever we're talking about plate tectonics, we always have to look at essentially a map of the Earth. Now, when we look at maps of the Earth, we tend to notice that there are natural boundaries or things like that that we actually can see, right? And right now, if we were in class, I'd be showing you the big map that's on the wall on the side of the classroom, and I'd be pointing out all of the mountain ranges, like the big ones that run up and down the west coast of North, Central, and South America. All right, the mountain range that essentially runs underneath the central of the Atlantic Ocean, amongst some other things. So, what is plate tectonics? Well, it is a theory. Now, it's a theory saying that the lithosphere, meaning Earth's surface, all right, lithos is the Greek word for rock, all right, so the lithosphere, Earth's surface, is broken into many large plates, meaning that the outer part of the Earth is not one big solid piece. Now, we know rocks are solid, yes, but they're not one connected piece, right? If you remember, the beginning of this topic was called, or the name of this topic was Earth's dynamic crust. All right, so the word dynamic means changing. So what is always changing? Earth's surface. All right, so along the boundaries or the edges of these plates, the lithosphere is either created or destroyed. Now, how do we see that? Well, there are several different occurrences that show us this. Now, for example, here in New York, we're probably not going to see many of these things. Why? Because we are not located on a plate boundary. Now, I'm just going to quickly jump to a map in our reference tables. Now, I know we haven't actually seen or looked at this yet, so welcome, here it is, right? But New York is right over here where I put that X. That is just about where we are. So since this is New York, actually, I'm sorry, a little low. I don't even know where we are. How about that? Okay, so sorry, New York is more like right there, so close enough. But do we have any plate boundaries near us? No, we have them kind of pretty far away, so we're not going to experience these things. So earthquakes, volcanoes, ocean trenches, younger mountain ranges. All right, so these are four different things that if you live where the tectonic plates meet together, you're going to experience this. For example, again, reference tables, page 6, I'm sorry, page 5, page 5, and here is that tectonic plate. So this again over here is us, right? But what is over here? Right? This is California. What is California known for? Well, California is known for their mountains. The Rocky Mountains run up the entire west coast of North America. California is also known for their earthquakes. The northwestern part of the United States over here is known for its volcanoes, actually. Right? And ocean trenches, well, we don't have them here, right? Places like the Philippines and Japan and even Alaska have these trenches, and we'll talk about those in a few minutes. Okay, but you are going to have all of these occurrences, right, at or near these plate boundaries. Now, it is a theory because we can't see the entire Earth. We can't fully see these boundaries. We see the evidence that is left behind when one of these things happen. Like when an earthquake happens and the ground literally shifts apart, we could see that crack in the ground, but we don't see how big it really is. Earthquakes don't always occur on the entire plate boundary. Like if you have an earthquake here in California, that doesn't mean it's going to be felt down here, right, which is part of that really same boundary. Okay, so there are three different types of plate boundaries. Now, what I'm going to do is I'm going to jump back to the reference tables, and if we take a look on the bottom, right, first thing I want to show you is this arrow here on the map shows the motion at the boundary. So the arrows show that. So if I just take a look at, let's say, the Southeast Indian Ridge, this arrow is pointing this way, this one's pointing that way. That means that this is moving apart. Okay, and if we look for that symbol, we see that this is a divergent boundary. Right? If we come over here, right, to let's say, let's take a look at the Aleutian Trench. Well, now we have two arrows pointing towards each other. Right? This is a convergent boundary, and then the last one say the one that affects most of us, is right here at the San Andreas Fault. One is pointing up, one is pointing down like that. So these are transform boundaries. All right, so they're moving past each other. Okay, we do have another type of boundary which is known as complex or uncertain. What is complex or uncertain means that we're not 100% sure what's going on there. We haven't studied it long enough to fully understand what's going on. So we see one of those down here in the Caribbean plate, right, and over here in the East African Rift are two really big uncertain boundaries. We know there's a lot of movement, right, but we don't know exactly what's happening. Okay, so let's break down these three different type of boundaries. So first one, take a look at it. Here's a picture. It shows the two plates moving apart. This is the side view. Here is the ocean, right? And here are one plate moving this way and one plate moving this way. This is what we call a divergent boundary, right? The plates are forced apart by upwelling magma due to convection. Remember all the way back in weather I said convection was going to come back? Here it is. Right, so because magma gets really hot, it wants to move up, so it pushes up here in the center, dividing these two plates apart, pushing them apart. This is a divergent boundary, right? Here, we look on the bottom, here is our divergent boundary, and they tend to look like this, right? Now, why do they look like this, not a perfectly straight line? Remember, rocks are not very flexible, so when it divides apart, it tends to crack and break in between. Right? So that is a divergent boundary, right? And not working. Okay. So next we have this one. This plate, these arrows are pointing this way, right? Like that. And these arrows, or this arrow is pointing this way. This is what we call a convergent or a colliding boundary, right? Two plates are going to collide, they converge. Now, generally what happens with these is one is going to subduct, right? And subduct sounds similar to subtract. It means go down. All right, so one is going to subduct below the other one. Generally, it's the oceanic crust subducting or going underneath the continental crust, and it generally creates a mountain range on land and a trench underwater. So what happens is, as this moves towards the continental crust is going to catch and it's going to kind of roll up because it's not going to just slide past each other. It's not going to happen very easily. And then as this gets pushed down, right, you're going to get a trench because you get that little area that gets literally sucked or pulled down. Now, why does the oceanic crust subduct beneath the continental crust? Continental crust is generally made up of the igneous rock granite, whereas oceanic crust is generally made up of the igneous rock basalt. And if you remember back to your reference tables, right, and I'll just jump to the reference tables because the igneous rock chart is right on the next page here, right? Here is our igneous rock chart. Here is granite and here is basalt. Granite is on the lower density side and basalt is on the higher density side. So that is going to cause the oceanic basaltic crust to subduct. All right, and if we look at it, right, let's say here is the Pacific plate, right? It's moving up this way, colliding with the North American plate. So we have two things moving into one another. And then if we look at the symbols here, these boxes are on the North American plate side. So if we look down at the bottom, it tells us that the side that has the boxes is the overriding plate, and the side that is clean, essentially, doesn't have the boxes, is the subducting plate. So the Pacific plate is going underneath the North American plate. If we jump over here, look at the South American plate and the Nazca plate, which is oceanic, is going to subduct underneath the overriding South American plate. And what mountain range goes up and down the west coast of South America? That is the Andes Mountains. Okay, that is a convergent boundary. Right? Then the final one, we have two plate boundaries that slide past each other. This is known as a transform boundary. So the two plates are going to collide. Now, that doesn't mean they're necessarily going to bump into each other going this way, but remember, this break here in this picture is not perfect. Everything doesn't just slide past each other gently, right? Nothing in nature on Earth is Perfect. So what happens is the two plates do collide and they do slide past each other, but pressure builds up and then the rocks are going to break and the plates are going to move. So the easiest way to kind of have you experience this is if you take your two hands and put them together in front of your face like you're essentially praying. Now push together as hard as you absolutely can. Now, while you're pushing together, try and push your left hand towards the ceiling and pull your right hand towards the floor. Notice they don't move. And then when they finally do move, they jump a lot and they break. And notice that there's a lot of heat that builds up. That is essentially an earthquake. That's what happens here, right? At these transform boundaries, right? That's why we have some bad earthquakes in California because of that San Andreas fault, right? And also parts of the Caribbean, like Haiti and areas that have earthquakes. Again, here is that transform boundary. All right, so those are the three boundaries. And we can see we have this is an earthquake, but this was an irrigation ditch that should move like that, but now it is not there, it's over here. This plate moved this way, and this one moved this way, right? This is in California, so this is the San Andreas Fault, right? We could also see parts of it here, right? Here is the fault, and this is where it shifts over, right? Should go straight up. Right? This was also very common when early settlers in the United States moved west. They'd build fence lines because we like to section off our property, right? And then you'd have an earthquake and the fence lines would move. This should be over here. All right, so that is the theory of plate tectonics, and it ties right into continental drift. Now, what does it mean to drift? Right? If something drifts, it moves, right? It doesn't stay in one spot, right? And a continent is a large mass of land. So when we take a look at our maps, right, continental drift is when large masses of land are going to drift apart. Now, these are just two cartoons to be a little funny. So like you could see in this picture, right, this land and this land have drifted apart like this. Now, this would never happen where a person and the dog would get separated like that because continents don't drift very fast, right? In fact, most of the continents move only a few centimeters every year, right? A few centimeters. So this is not going to happen, right? And we can see here, right, we are drifting apart, right, and one side is laughing at the other, running away. Now, again, doesn't really happen that way, but that's just to kind of help you think about it. So, what is continental drift? Well, here are our plate boundaries. Here is our divergent plate boundary. Here is our convergent plate boundary, and it's causing all of the continents on Earth to move, right? It's an idea. We see these things moving, right, very, very, very slowly. And it's not something that's just taken out of thin air. We actually have evidence that supports this. So the first should be the most obvious. If you take a look at a picture of the Earth, right, here are all of the continents. If I gave this to you when you were 4 years old, 5 years old, and said that this was a puzzle, right, you would then start going, okay, let's put all this together, right? So Africa would kind of shift over this way, fit next to South America. North America can kind of shift over here. Australia would shift right up in here, right? Madagascar could shift over, right? So the continents seem to fit together. And here's a rough image of it. Now, is this perfect? No. Why don't the edges of the continents fit perfectly together? And yes, I understand they're not all here, but these show it really good. Why don't they all fit together perfectly? Well, over hundreds of millions of years, the ocean has taken its toll. Erosion and weathering have broken down the edges here so they don't fit perfectly together. But again, go back to this map. These two look like they're pretty darn close to each other. Same thing here. All right, so the continents really do seem to fit together. Right? So going back, right, to the Permian period, roughly 225 million years ago, we had the massive supercontinent Pangaea. So here's North America, South America, Here's Africa. Here is Eurasia, right? This is actually India. Here's Australia, and this is Antarctica. And things started to break apart, right? Roughly in the Triassic, early dinosaurs. We had 200 million years ago, Gondwanland, which was the southern supercontinent, and Laurasia, which was the northern supercontinent. And then we slowly started to break apart until what we see today. Now, how do we know that this occurred? Nobody was around 225 million years ago, but we have evidence, right? And some of this evidence is indicated in this picture. We see different forms of animals and we see plants. We find their fossils across the different continents. So, what does this mean? And it's not just fossils, rocks, mountain ranges, fossils, glacial deposits, and even mineral deposits match across the oceans to where the continents fit together. So going back and taking a look at this picture, Cygnagathus, right, which was about 3 meters long, so you figure maybe about the size of, let's say, a horse, okay, right, really, really short legs, found in South America and Africa. So you're going to tell me, right, that this animal can swim across the entire 3,000-mile Atlantic Ocean with these tiny little legs to get to Africa, or vice versa. No, it's not going to happen. All right. Same thing over here, Lystosaurus. Right, this guy was about the size of a rhinoceros. Right, he was found in Antarctica, India, and Africa. Well, what lives on Antarctica today? Nothing. It's frozen. It's a giant mass of ice. It is super, super cold. All right, and it is very far from all of these continents. Yet, its fossils are found there. All right, fine. Maybe you're thinking, okay, somehow an animal got there. How about plants? All right, Glossopteris is found on Australia, Antarctica, India, Africa, and South America. So this plant has traveled all the way around, essentially the entire southern part of our Earth. How many of you have ever seen a plant walk? How many of you have ever seen a plant fly? None, right? Even if a plant gets picked up in the wind, traveling these distances would be impossible. Okay, so this supports that idea that the continents were together. All right, now the next thing we have are mountain ranges. Well, we have old mountain ranges that make up the eastern part of the United States. Well, these rocks here, or sorry, North America, these rocks here are identical to the rocks that are found in Northern Africa, Southern Europe, right, and even parts of Northern Europe, right? They match together, right? And it's the same thing down here in Southern Africa. South Africa matches up with this small area over here in South America because they were connected. And rocks don't fly, walk, or move on their own. Okay? Next, all right, another piece of evidence. All right, so remember, we have the continents fit together, then we have fossils, mountain ranges, rocks, things like that support it. Another thing is magnetic properties of rocks as they cool. All right, so when we have igneous rocks as the magma and lava cools is going to have magnetic minerals in it. Well, the magnetic minerals are going to line up with Earth's north and south pole, very similar to a magnet. That's how magnets work. Over time, at mid-ocean ridges, right, as these plates diverge apart, right, you have new magma flowing up here in the middle. What happens? As that magma cools, the minerals solidify and they indicate the polarity of Earth's north and south poles, meaning where they are. But notice as we go farther back, right, as we go from, or sorry, as we go more towards today, we're 4 million years ago on the bottom, on the top here, as we work our way closer to today, we notice that the polarity changes from negative to positive to negative to positive at that boundary. And we have the same on each side. Notice that this pattern, let's take a look at the bottom, this pattern here is the exact same thing as this pattern over here. Why is that? Because they're dividing apart at the same rate, right? Now, how do we know that everything is moving apart? Well, the rocks indicate that. If they weren't the same on both sides, we wouldn't see that, right? And the polarity lines up. So Earth's north and south pole have switched every it's, I believe, every roughly 10 to 20,000 years or so, Earth's magnetic north and south poles switch, meaning the polarity of it. So the magnet inside the Earth switches. Okay, what this causes is ocean or sea floor spreading. Now, it's kind of seen here, but when the ocean floor spreads, it's rifted or spreads out over time. So what does this mean? Right? Rifting will only occur along mid-ocean ridges and underwater. So I'm just going to jump to the reference tables. So if we look at this, East Pacific Ridge, Mid-Atlantic Ridge, Southeast Indian Ridge, Southwest Indian Ridge, these are all divergent plate boundaries. So what's happening here, right, is the magma, right? Let's pretend, actually we could just go back to this. What's happening at these boundaries, right, is the plates are dividing apart. Magma is pushing up here, causing these plates to shift. Now it's called a ridge because a ridge is like a small mountain range. So rifting only occurs here, so ridges, right, are underwater mountain ranges. So the largest mountain range in the world, right, is the Mid-Atlantic Ridge because it runs from the North Pole down the entire Atlantic Ocean all the way to the Southern Ocean. That doesn't mean it's the tallest, but it is the longest. All right. So as the distance from the mid-ocean ridge increases, the age of the bedrock is going to increase, meaning it gets older. So, again, if we take a look at the mid-Atlantic ridge, everything right here is young because it's occurring, it's forming today, right now. But as we move this way, let's say towards New York, the rocks here are going to be much older than the rocks here. In fact, the rocks here are several 100 million years old. These might be several minutes old. All right. So again, as the distance from the mid-ocean ridge increases, the age of the bedrock is going to increase. So only at mid-ocean ridges do we have this seafloor spreading. Right now, we could see it in this little animation. Magma is pushing up here, forcing the plates apart. This plate is moving this way. This plate is moving this way. So this here is going to be young, right? And the farther we get over here, this is old, but this is also going to be old, right? And this pattern is going to match this pattern when it comes to that magnetic polarity because they are the same. They're forming at the same time, right? And this is very common, very commonly what it looks like. So here's what I said. This should be a straight line up and down, but because rocks are not very elastic, are not going to bend, they tend to break and shift along these boundaries. So you get these kind of broken areas, which is why we see these kind of shifts like this. The black and white pattern on each side, right, is the indication of the magnetic polarity. So notice this pattern over here is the same as this pattern over here. All right. Here's how the Atlantic Ocean formed. If we go all the way back to Pangaea, there was no Atlantic Ocean, right? Then we had magma pushing its way up, creating this bulge, pushes the continents apart. Now we have what's called a rift valley, right? We see rifting where it pulls apart. The ocean starts to flood in because it's a lower area, right? And now you have the Atlantic Ocean and the mid-ocean ridge. All right, and this is kind of what it looks like, and I'm not sure why it's not working. Right, it's not working. Right, and again, let's see. This one's not working either, but it should show you that it pulls apart. Okay, so again, if we take a look at this, this is actually a very common type of regions question. This is where we're going to end with this. But if you're given one side of this, and you have to either draw or pick an answer choice that is missing, you would have to make this pattern match up. So this would have to look exactly like this side does, essentially like a mirror image. Okay, that's how it works. All right, and again, make sure that you're looking at this page in your reference tables. It gives us a lot of extra information. All right, with that, that completes the second and actually third parts of this topic. All right, but the plate tectonics and continental drift kind of go together. Again, if you have any questions, feel free to reach out to me on Teams or send me a message.